Now it's recording. It just said. So do you think it's recording? It said it was
Uh,
recording. It said it was.
yeah, I know, but I don't have. Normally, you have that bar, and there's a little. Oh, it's up. Okay, here we go.
Well, try starting the slideshow and see if it tells
Yeah,
me that it's recording me.
it's okay now. I think. I don't know, it's behaving very weird today.
Hmm.
Okay, so we're going to talk more about feedline connectors, the connector portion. The most commonly used coaxial connector in amateur radio, at least, is called a PL259 or an SO239. One is a male connector, one is a female connector. They call them UHF connectors, but they're really just VHF connectors. Um, Another common one is a BNC, which is we call a bayonet type. It's actually a push and twist and it locks. So they're very easy to connect and disconnect. Uh, you find those used a lot for hooking up test equipment and things like oscilloscopes and signal generators, things like that. There's an SMA connector, which are very small threaded connectors, about a quarter of an inch in diameter. They go up into the high gigahertz range. You see them used inside of a lot of radio equipment to make connections. There's a type N, which is better for UHF, and they claim to be waterproof. I'd say they're water resistant because of the way they uh, connect together. They're much more expensive than the PL259s. So that's why the PL259 is the most common one. Even off of Amazon, an N connector is at least twice as much as a PL259 connector. And if you get it from uh, Times Microwave, they're $20 to $30 as opposed to two. You see this chart?
Hmm.
Okay. These are not exactly to scale, um, but I didn't make the chart. So you can see there that the SMA connector goes up in the 18 gigahertz range. Next is the N connector, which is much larger than is shown there. Um, there's another variation called a TNC, which I'm not really familiar with. I've only seen pictures, same as the SMC. The little MCX, which is much smaller than what's shown there, is usually what they use inside of um, I'm not sure about cell phones, but laptops, iPads, things like that to connect up to uh, their little antennas. These are very, very small snap-on connectors. There's a BNC, which I said is mostly used for test equipment leads, laboratory type stuff. And then down at the very bottom right is your PL259, which they're showing up in the between 300 and a gigahertz. Um, N connectors are preferable when you're talking UHF and above, particularly for outdoors. So which of the following is true of PL259 type connectors?
Farley.
Which of the following RF connector types is most suitable for frequencies above 400 megahertz?
Bravo.
Let's see. I guess the main thing here is when you're doing connectors on a coaxial cable, whether they're crimped or soldered, you need to ensure that they're crimped properly or soldered properly. You need a good connection. If you've got a loose connection, you can get some very high or rather erratic changing SWR. And you also need to make sure that when you connect these connectors together that you have a good solid tight connection. And if it's outdoors, they need to be sealed with tape. They sell special stuff for sealing coax connectors, but all I've tried sucks. It's much better to use some good Scotch, like 33 electrical tape, and then a coating of the rubber type electrical tape, and then other plastic tape on that to protect the rubber from the ultraviolet. And you put the first layer on because if you have to take it off, it keeps the rubber tape from kind of welding itself to the connector. You can peel it off if you've got the first layer out of regular plastic tape. What can cause erratic changes in SWR?
Bravo.
Okay, we talked about standing wave ratio. So it's a measure of how well the antenna is matched to the transmission line. So if you had a perfect match, the antenna was 50 ohms, your feed line is 50 ohms, your transmitter is 50 ohms, you're going to have an SWR of 1 to 1. If you had an SWR of 1.5 to 1, that's typically okay. You get a little bit of reflected power back, but the loss isn't that much. If you get to 3 or higher, most modern transceivers will actually start reducing power because those high SWRs can damage the output transistors on the modern radios. So they have a safety circuit in there that looks at the SWR and will start reducing the amount of power that it puts out the higher the SWR goes. Typically starts at 3 and above. These you don't need to remember. It's just showing you how SWR is calculated. And there's a lot of different ways. It's the ratio of the maximum to the minimum voltage, or the maximum to minimum current, or it's the ratio of the load to source impedance, or source to load. Whichever one is greater, you always have the bigger number first. So it would never be 1 to 2. It would be 2 to 1 or 3 to 1, 1.5 to 1. But like in the example here, you might have an antenna that is only 33 ohms, and you're feeding it with a 50 ohm source, so you're going to have a 1.5 to 1 SWR, but you still operate okay with that. So what is standing wave ratio?
Alpha.
Is that what you said?
I did.
Okay.
Can you hear me okay? Do I need to speak up or
Well,
anything?
I think it's my speaker. It's slightly distorted. What reading on an SWR meter indicates a perfect impedance match between the antenna and the feed line?
Charlie. Charlie, Charlie, Charlie.
What does an SWR reading of 4 to 1 indicate?
Delta.
Okay. SWR will be low when you've got a good impedance match, which means you're pretty close. And it's going to be high when you're not close. So the higher it is, the more power you're going to lose in the transmission line as a result of heating. Because that reflected power comes back through that transmission line. So you lose power going up. You lose power coming back due to the loss in the transmission line and heating. When it gets back to the transmitter, it may get reflected back, and it's going to keep bouncing back and forth until it's totally dissipated. So all of that reflected power winds up as heating in the coaxial cable. So obviously the more reflected power, which means the worse match, the more heating you're going to get and power loss in the coax. This is trying to show, if you look at the blue line, which is our original signal that we're sending to the antenna, and it gets up to the end and it's not a perfect match. So we have this red, which is the reflected amount. It turns out it's always going to be out of phase. So when you add the red and the blue, you wind up with this black line, which is the standing wave. So the higher this, or the stronger this reflected signal is when it adds to the transmitted signal, the higher the standing wave is going to be. And it can turn out to be much, much higher than the signal you're actually sending. So what's the benefit of a low signal to standing wave ratio?
Bravo.
What happens to power lost in a transmission line?
Charlie. Charlie?
Right. Okay. I talked about modern transceivers tend to reduce power if you're above 3 to 1 SWR. That wasn't a big problem with older radios that had tubes, or as the English say, valves. as their power amplifiers, but most of the modern radios use field effect transistors, which are much more sensitive to high voltage transients, which you can get from high SWR coming back, because the transmitter sees that reflected wave coming back.
Oh.
Why do most modern solid-state transceivers reduce output power as SWR increases above a certain level?
Alpha.
Okay, so a lot of people buy SWR meters so they can monitor how good a match they have to their antenna. Now, some of the radios will actually have a built-in SWR meter, and in a lot of them they'll have a antenna tuner. Doesn't tune your antenna, it just is a matching device to make the SWR appear much lower to the transmitter. It'll still be whatever it is out at the antenna, but what the transmitter sees will be a much lower SWR and maybe even look like a perfect match. So if you're looking to buy an SWR meter, you need to make sure that you're getting one that operates over the frequency range that you're going to operate in. In some cases, they'll be switchable, and they can monitor HF and VHF, UHF by changing a switch. In some cases, they're fixed, and you have to buy a separate one for HF frequencies or a different one for VHF or UHF frequencies. You also need to ensure that it's rated for the power that you're going to transmit. If you have an external power amplifier, say putting out 1500 watts, then you need an SWR meter that's capable of running 1500 watts. If you're trying to measure or use it at 1500 watts and it's only rated at 100 or 200, you probably damage the meter. Some meters will just show you, particularly some of the more modern digital ones, show you just SWR. In some cases, they'll show forward power and reflected power as well as SWR. There's some analog SWR meters that's actually two analog meters with pointers or needles. One is showing the amount of forward power, the other is showing the amount of reflected power, and where they cross, you find markings on the placard behind them to show you what the SWR is. Those are a little hard to read. I have a couple of each. I kind of like the digital one that shows me SWR, forward and reflected power. In fact, I have one just like the one on the left, except mine's an MFJ because they're all made in China under different names. Over on the right is the cross needle type that I talked about. And you can see the markings here, which are SWR. So where these two needles wind up crossing, whichever one of those lines it is the SWR. So it shows you forward and reflected, and these lines are calculated based on the ratio of those. So which of the following should be considered when selecting an accessory SWR meter?
Alpha.
You can also measure SWR with a directional watt meter. One of the kind of industry standards is a bird, and it measures either forward or reflected power. You have to switch it back and forth. So it'll show you how much forward power. You flip the knob and it shows you how much reverse power. And using those, you can actually calculate the SWR using this formula down below, which you don't have to remember. But it's basically showing the ratio of the forward and reflected. And it's set up such that if you have a forward power of something and reflected power of 0, it will give you an answer of 1 to 1, which is why it looks kind of funny. And they're using the square roots. Which instrument can be used to determine SWR?
Delta.
Where should an RF power meter be installed?
Alpha.
Okay, another tool is called an antenna analyzer. Can also measure SWR, but it can do other things and show you whether or not your antenna is resonant at a particular frequency. In some cases, they can also measure capacitive and inductive reactances. They can be used as an RF signal generator. So a lot of capabilities. Over on the left is an old MFJ. I don't know if anybody's still making those because MFJ went out of business, but it was a popular SWR antenna analyzer, used analog meters. So basically that's all it would do was kind of show you the SWR and impedance. So you could use it to tune your antenna, try to get it to resonance. Over on the right is what's called a nano VNA. It's a vector network analyzer. And these came out, I don't remember, not all that long ago, where you used to have laboratory grade vector network analyzers that were big pieces of test equipment that in some cases could cost $100,000 or more. This little thing, this nano one, you can buy for $80 to $100. It's not as good as a $100,000 one, but what you need is more than adequate, and it does all the same stuff. Not as accurate, but it's a heck of a lot cheaper. So which of the following is used to determine if an antenna is resonant at the desired operating frequency?
Bravo.
So, like I said before, if your antenna is not 50 ohms, then the transmitter is not going to see a 50 ohm load. So that's why you use these, what and I don't know where the name came from, antenna tuner, because it never tuned an antenna. It's just a matching device or coupler that allows you to make the transmitter see 50 ohms when the antenna is not. And we call that impedance matching, not antenna tuning. But it's stuck around, and they still sell antenna tuners. Here's a little MFJ, little portable one that you'd use for like QRP radio, low power stuff, where the knob over on the right hand side is just adjusting the inductance with a switch that's different taps on an inductor that's in there, and the two knobs over on the left are changing tuning capacitors. So that's how you're adjusting that network that's inside the box to make your transmitter think that the antenna is 50 ohms or close. So what's the major function of an antenna tuner or coupler?
Alpha.
Okay, the next piece of test equipment that's handy for test purposes is a dummy load. And it allows you to basically simulate an antenna. It looks like a perfect resistive 50 ohm load for a wide range of frequencies. This one shown here, actually I think that's the same one I have. It's capable of handling 300 watts for a short period of time. And it'll go up to like 650 megahertz, so it covers most of the amateur frequencies, even the VHF and UHF. So it allows you to make adjustments to your transmitter without actually sending a signal over the air. You just connect your transmitter up to this dummy load instead of the antenna. So it has purely resistive resistors inside, typically mounted on some sort of heat sink, which is why it can only take 300 watts for a short period of time. And on the back side of it is a little scale showing you how long you can operate at different power levels before it overheats. But normally you don't need to run it very long. What's the primary purpose of a dummy load?
Alpha.
What does a dummy load consist of?
Bravo.
Okay. So we learned about PL259s and also SO239s, which is the female part of that connector. For type Ns, they work best up in the UHF range. There's a type N male and female. They just don't have different numbers. It's just an N male or an N female. We learned what SWR was, that a high SWR can be a result of a loose connection on one of the connectors or maybe a bad crimp or solder joint. That an SWR 1-to-1 is a perfect match, means it's purely resistive and it looks like 50 ohms. If your SWR is below 1.5-to-1, it's a good enough match to operate. You're not going to have much signal loss. If it's very high, you can actually damage the transmission line, and you could possibly damage your transmitter unless it starts reducing power. We can measure SWR with an SWR meter or a directional watt meter or an antenna analyzer. We can, quote, tune my antenna or match the antenna with an antenna tuner. And we can use a dummy load to test without actually operating on the air.